Thanks very much. Next paper is also an online presentation, but the last one in this session, Meissa, and we have two real presentations, Meissa, Scalable Network Testing for Programmable Data Planes. The presenter is Neiqian Zheng, who is a rising first-year PhD student at Peking University, interested in large-scale networks and systems, especially their correctness and reliability. Over to you. Thank you.
Hello everyone, I am Neiqian Zheng. I just received my bachelor degree and work for a PhD in Peking University. Today, I'm glad to share our work, Meissa, Scalable Network Testing for Programmable Data Planes. This is a joint work with Kaicheng, Xuanzhe, and Xin from Peking University, Mengqi, Ennan, Hongqiang, and Yifan from Alibaba. Recent years, programmable switches are popular in data centers and edge networks. They have strong flexibility to hold various network functions, such as firewall, NAT, and load balancer. Developers often offload these network functions to programmable switches for better performance. Programmable data planes are versatile, and they have high performance and flexible programmability. However, these properties lead to new challenges. In our industrial practice, developers are greedy with performance of programmable switches. The control flow graph of P4 programs is usually very large. As an emerging language, P4 has a considerable number of bugs in its toolchain hardware. Besides, due to lack of testing tools, data plane programs are usually incomprehensively tested. Bugs are common in the development and operation of programmable data planes, but they are very detrimental. In the past years, bugs in programmable data planes even made our entire load balancing service down. We need a comprehensive, automatic, and scalable network testing toolkit to help us identify bugs. According to our experiences, bugs can be classified by sources. They are code bugs and non-code bugs. Code bugs include code logic bugs and table room misconfigurations. We know doubtful works do not test configurations together with P4 code, such as P4 packet gen. But in our experiences, configurations actually build a control flow graph together with P4 code. So we decide to model configurations and P4 code at the same time. Non-code bugs include bugs in the toolchain and bugs in the hardware target. For example, compiler bugs and incorrect compilation flags are non-code bugs. You will be familiar with them if you have some experience in P4 development. Non-code bugs are more difficult to identify and resolve because developers are usually unfamiliar with compilation settings and compiler implementations. To identify these bugs, researchers have proposed many tools based on verification and testing. Verification, such as Aquila and P4V, is able to identify code bugs, but they do not check non-code bugs. Testing, such as Gauntlet and P4 packet gen, provides comprehensive bug checking ability, including identifying non-code bugs. However, the number of possible paths grows exponentially with the size of a program, which is widely known as the path explosion problem in the literature of software testing. One of P4 programs in our production edge switch consists of 10 to the power of 4 lines of code, and the number of paths is 10 to the power of 197. The state-of-the-art testing techniques suffer from path explosion, and they can hardly scale to large programs. Thus, the biggest technical challenge is to identify both code bugs and non-code bugs for large-scale programs. Meissa is a scalable network testing toolkit for large-scale programmable data planes. Compared with the state-of-the-art techniques, Meissa has better scalability and bug checking ability. This is the overview of Meissa. Operators take their P4 code, table entry rules, and specifications as inputs. Meissa models them into a control flow graph, generates test cases, emits testing packets on testbed switches, and outputs a test report. For better scalability, we propose a domain-specific code summary technique to simplify the control flow graph before generating test cases. Code summary is the core of Meissa. Okay, we'll talk about control flow graph, test generation, and code summary respectively. The control flow graph depicts logics of a P4 program, which consists of code logic and table entry rules. We model P4 logic with predicate nodes and action nodes. Predicate nodes are for table matching and branches, such as an if statement. Action nodes are for variable assignments, such as assigning a new TCP destination port. Here is an example. The if statement is encoded into predicate nodes, and the assignments are encoded into action nodes. The task generation is to generate input packets which traverse all paths in the control flow graph. Meissa leverages the DFS to traverse the control flow graph, and the symbolic execution to check the path satisfiability and to generate a corresponding input packet. Symbolic execution is widely used in software testing. It collects symbolic context of each path in the control flow graph, combines the conditions, and emits conditions to SMT solver to check whether the path is satisfiable. DFS and symbolic execution cannot scale to large programs. So we need code summary technique to simplify the control flow graph before generating test cases. Programmable data plane follows a pipeline layout. The example program has an ingress pipeline and an egress pipeline. Each pipeline has a lot of tables. We know that not all compositions of table rules are valid. So there are both valid paths and invalid paths in each pipeline. Here comes the problem. When we conduct DFS on the control flow graph, 900 invalid paths in the egress pipeline will be checked invalid for 90,000 times, because valid path in the ingress pipeline repeats its procedure for 100 times. It's a big waste of time. This redundancy even explodes as a combination of pipelines in large programs. One straightforward idea is to remove invalid paths in the egress pipeline in advance. This is our inspiration. With these observations, we propose a domain-specific code summary technique to simplify the control flow graph before generating test cases. Firstly, code summary decomposes the control flow graph into individual pipelines. Secondly, code summary simplifies code logics of each pipeline by removing unsatisfiable paths. Finally, code summary updates control flow graph with simplified logics. When all pipelines are simplified and updated, the entire control flow graph will be ready for test generation. At a high level, the summary removes invalid paths and encodes each valid path with its constraints and variable values compactly. We note that similar ideas like code summary have been proposed to generate test cases for general-purpose languages. However, they are mainly targeted at function calls, where the vertical composition of components makes it hard to simplify lower-layer library functions. In comparison, programmable data planes follow a pipeline layout. Meissa leverages its horizontal composition of components and adopts domain-specific techniques to significantly simplify each individual pipeline before generating test cases for the entire program. The most important part of code summary is to simplify an individual pipeline. Let's start from an example. There is a P4 program among two pipelines in the programmable switch. Pipeline 1 encapsulates packets into VXLAN, and Pipeline 2 has both TCP logics and VXLAN logics. As mentioned before, both Pipeline 1 and 2 have a lot of redundancy. We are going to simplify the control flow graph with code summary technique. Our methodology is to simplify Pipeline 1 and Pipeline 2 respectively, and thus the entire control flow graph is simplified. Firstly, we use intra-pipeline redundancy elimination technique to simplify Pipeline 1. Intra-pipeline redundancy elimination is to remove invalid paths inside the pipeline. It should also keep all valid paths and their contexts. Meissa leverages the DFS on the pipeline CFG, and meanwhile, a symbolic execution to collect the contexts. After the DFS, all invalid paths are removed, and valid paths are rewritten by combining their predicate nodes and action nodes into summaries. Thus, Pipeline 1 is simplified into a compact summary one. Next, we are going to simplify Pipeline 2. Similar to Pipeline 1, we can use intra-pipeline redundancy elimination to remove invalid paths in Pipeline 2. But it seems that we miss that all packets after Pipeline 1 are VXLAN. Intra-pipeline redundancy elimination only has an intra-pipeline perspective. it has no idea about what the packet sent to the pipeline might be. So we can use that inter-pipeline technique to further simplify pipeline 2. Inter-pipeline public precondition filtering is based on the observation that intra-pipeline redundancy elimination is incomprehensive due to its intra-pipeline perspective. In this case, pipeline 2's TCP logics are reserved after intra-pipeline redundancy elimination because they are valid in pipeline 2. But they will be never visited because all packets sent to pipeline 2 will never be TCP. We define public precondition as a common condition shared by the path from the entry point of the program to the target pipeline. In this case, VXLAN is the public precondition of pipeline 2, and the logics of TCP will be removed from pipeline 2's summary. To solve public precondition of the target pipeline, Meissa leverages the DFS and symbolic execution to get the conditions of all paths from the entry to the target pipeline. After that, the common conditions are for pruning, and the target pipeline will get further simplified. With both two techniques of code summary, intra-pipeline redundancy elimination and inter-pipeline public precondition filtering, pipeline 2 is simplified into summary. Note that in this case, pipeline 1 has no preconditions, so we only conduct intra-pipeline techniques to summarize it. We can also set constraints in the specifications as precondition of pipeline 1. We evaluate Meissa on 4 open source P4 programs and 4 P4 programs in our production network. Gateway 1 to Gateway 4 are programs inside our global network. The largest program is over 20,000 lines of code and among 8 pipelines in 2 switches. On open source P4 programs, Meissa is up to 400 times faster than P4 Packet Gen and Gauntlet. P4 Packet Gen and Gauntlet do not support some functionalities in our production programs, so we only compare with Aquila on last 4 production programs. On Gateway 1, Gateway 2, Meissa is up to 26.5 times faster than Aquila. On Gateway 3, Gateway 4, other techniques cannot finish in 1 hour time budget. We also evaluate the bug finding ability of Meissa. Compared with P4 Packet Gen, PTA, Gauntlet, and Aquila, Meissa successfully identifies both code bugs and non-code bugs. Meissa is able to not only detect known bugs, but also previously unknown bugs. Since fall 2021, Meissa has been deployed in more than 200 P4 gateways among 4 continents in the world. It identified tens of bugs and prevented hundreds of potential failures in our global network infrastructures. In our production networks, Meissa successfully identified real bugs which could not be detected by existing tools. Our developers once set an incorrect compilation pragma on a large P4 program in our production network. This incorrect pragma made 2 packet fields incorrectly overlapped, and the ACK number of the output packet was wrong. This is a non-code bug because the logics and tables are correct. This bug was not detected by our manual test cases because they were incomprehensive and did not cover logics triggered in this bug. Verification techniques did not detect it because they could not detect non-code bugs. Existing P4 testers did not detect this bug because it did not scale to large programs. Meissa is comprehensive and scalable, and successfully generated test cases for all paths and thus detected this non-code bug. In a word, Meissa is a scalable network testing system for programmable data planes. The domain-specific code summary technique strongly speeds up test generation, and it is also proved to keep 100% path coverage theoretically in our paper. Meissa is developed for programmable switches, but its principles also apply to other programmable data plane devices. Thanks for listening, and feel free to raise any questions. Thank you.
Thanks very much. Thank you. There's a question here, and Stefan first, and then back there, which I can't see you, sorry, it's in the dark. Introduce yourself.
Stefan Smolka from Google. Thank you for the great talk. So you talked about these code summaries. I'm curious, what kind of data structure or encoding do you use to encode these code summaries? How does that work?
Well, actually, we just leverage the DFS and some simple execution. And after that, we know that some paths they are valid and other paths are invalid. So we remove the invalid path, and for the valid path, we just to reconstruct the CFG with our predicate nodes and action nodes, and some some directed in this way we can get a simplified CFG. This control flow graph is a little bit similar as the previous one we just generated from the P4 code and the table entries.
Thank you. Next, please.
Hi, Apoor from Huawei. Great talk. I have just one question. Do you also take care of the controller-induced bugs, like it was discussed by BF4 in, I think, 2020 SIGCOMM'? So do you also take care of those?
Yeah. Yes, thank you. I think that's a very good question. We just consider about whether to try to test the control plane bugs. But we just find that our method, our work, only tests stateless bug in the data plane, and the control plane bugs are usually stateful. For example, the reaction after a packet may be wrong, and that will result in an incorrect configuration. But we found that just testing the stateless bugs is difficult enough, and testing stateful bugs, especially the stateful bugs in the control plane, is very difficult for us to finish this in our the first version of our tester. So maybe in the future we will consider about testing the stateful bug and together with the bugs in the control plane. Thank you.
Okay, thanks. And one quick one, do you also take a look at all kinds of possible packet header spaces? What are the packets that are coming, looking at the tables, or just you focus on the code and the tool chain?
Yes, actually both. Yeah, we just enumerate all the packet types all the packet types from the parser, and all the packet types the parser which it supports, and which we also we will test them, and we also enumerate all the paths in the control plane of we also test all the paths in the control flow of our P4 program, and the parser is a part of the P4 program, and when we enumerate all the paths in the parser, so we can enumerate all the packet types in the packet header. So that's our solution. Thanks.
Okay, thank you.
Cool, thank you very much. Any other burning questions? Great, let's thank the speaker one more time. Thank you.
Okay, thank you.
Well done. At the end of my bachelor, I had not even read a paper, let alone have a SIGCOMM paper.